Hey, how you doing? I kind of forgot that I said I'd make you a video, but here it is. Um, should still be plenty to get you ready for Wednesday. You'll have maybe some of you will see it tonight, and you'll have Monday to look it over too. Sorry about the lateness. I'll try to get them out sooner. But I think what I want to do is go over this thing, the corrective assignment number one. I'm going to leave corrective assignment number two for you. You've got the answers, but not necessarily the how-to. But if you need to know the how-to, then just come see me for help, and I'll help you out. But let's start with number one. Number one was this question about the beach, where there's two sort of opposing functions. The first function R is modeling how the tide is taking sand away, so the R is removing. And then S is how there's a pumping station that's trying to add sand back onto the beach to sort of fight the erosion. So it says both R and S have units of cubic yards per hour. Cubic yards is just yards with a little 3 on it. So cubic yards per hour would be cubic yards per hour. The units would look like that. And T is being measured in hours from 0 to 10. So find the rate at which the total amount of sand on the beach is changing at time 6. Now, notice that R is already a rate function. So literally all you have to do is plug in 6. We just want to figure out what R of 6 is. You don't have to take a derivative. R is already a rate of change. So it's going to be 1 plus 6 times the sine of, if I plug in 6, it's going to be what, 12 pi over 25? And we get a little bit lucky here because this is not a sine expression that I can simplify. 12 pi over 25 is just some crazy angle. I don't know how to evaluate it. So I'll go to my calculator and I'll just do it there. And I can bring that up for you. Here's a calculator right here. And let's make sure that we're in radian mode. So click mode, and we are. Anything else I have to change here? I don't think so. So I'm going to clear all this junk. And what you can do is enter in your R function. It's 1 plus 6 times the sine of 2 pi x divided by 25. And if I enter all this like that, it'll be fine because it'll do all this multiplication in the numerator first and then it'll divide. I don't really need any extra parentheses for this. But now that that's entered, I can just go into my table, which I guess is already set up for ask. Again, if you don't remember, you can set your independent variable up for ask. Then when you go to your table, instead of it auto-completing, you can ask for whatever you want. And we want the value at 6, so enter 6. Now I see enough of this decimal, but if you remember, if you highlight it, you can see the full expansion. But 6.988 is fine. I only want 3 decimal places. So I'm getting 6.988 cubic yards per hour. And again, this is coming out positive, but we know that from the definition of the equation, this is still represents us losing this much sand. This is still the sand going away, which would sound like it would normally be a negative rate, but they framed this as removing, so they don't need a negative sign. We already know that it's taking away. All right, now for the next one. S of t is trying to add the sand back in, and again we would just find S of 6. And that's going to be 18 times 6 over 1 plus 4 times 6. And this math we can do out. This shouldn't be hard. I'll quit to the home screen. I'll do 18 times 6. I'm getting 108 in the numerator. And in the denominator we're getting 24 plus 1 is 25. So that's a fraction that doesn't reduce. It is okay to just give it as a decimal though. So 108 divided by 25 is 4.32. This is the one time you don't have to give me all 3 decimals, is this one actually terminates. You don't have to say 4.320 if the decimal terminates. You only have to say 4.320 if there's more decimals after the 0. But here we can stop and say cubic yards per hour. All right, now they're asking us, what's the total amount of, or find the rate at which the total amount of sand on the beach is changing at time t equals 6. Well, we are losing sand So we would want a negative rate. So technically we would do the 4.32 minus 6.988. We'll subtract in that order because we want to get a negative answer here, indicating that we're losing sand. So I'll subtract 6.9 and I'll get negative 2.668 cubic yards per hour. And that's it. So find the rate. Yeah, it doesn't say anything about interpret your answer or anything, but if it did, you'd write a sentence that says, when time equals 6, we are losing 2.688 cubic yards of sand per hour. That's what's happening here. So at the 6th hour, the pumping station is not keeping up with the rate of loss. That's the idea. All right, number 2. Number 2 is another one of these table of values problems. It says tourists visiting an island contracted a mystery illness over a 45-day period. The health authorities recorded the rate of new cases per day, and some of the rates are listed in the table below. Use the table to estimate n prime at 20. So we don't have 20, but we know that 20 would fall here between 15 and 25. That makes this one pretty easy. We know that we're going to estimate that instantaneous rate of change at 20 by finding the average rate of change from over the interval for the two values on either side. So let me just get this out of the way for a minute, and we'll do that. So we're going to say that n prime of 20 is approximately equal to the average rate of change, which would be n of 25 minus n of 15 over 25 over minus 15. And that's giving 100 minus 30 over 10, which is 70 over 10, which is 7. And what would my units be? Well, let's see. N of t, my y variable, is new cases per day. And my time is day. So this is a rate. This is a rate of a rate. Health authorities record the rate of new cases per day. Yeah, I guess so. So this is going to be 70 cases per day. Which you could literally write as cases per day. But that seems a little weird. Let's just say 7 cases per day squared. That's the notation we've been using. Let's stick to it. Okay, so now we can do part B. So let me get all this stuff out of the way now, I guess. We'll bring back part B, which says, after studying the spread of the disease, the health department authorities decided they could model the number of new cases with the model R of t equals all that stuff for 0 to 50 days. The disease is considered eradicated when the number of new cases per day does not exceed 5. Use R of t to find on what day this will occur. Okay, so this is the one we said where what we would want to do is take R of t, this whole big complicated equation that they came up with, which is 80,000 times e to the negative 0.2 t all over 1 plus 200 e to the negative 0.2 t all squared. And what we want is we want to make sure this is not greater than 5. So the moment that this is less than or equal to 5, whatever value of t causes that to happen is the answer. And we said that, no, I don't think we want to try to solve this by hand. Do I have any interest in trying to solve this by hand? Not really. Even just taking this thing here and squaring it already seems like a pain in the butt. So that means what we should do instead is just bring on our calculator, which happens to be sitting on the screen already. I meant to turn that off, but I didn't. So anyway, let's go to our calculator. What I would do if I were you is clear everything, go to y equals, and I would enter this equation. So very carefully I would enter, how would I enter this carefully? Isn't math alpha a thing or something? Math alpha math? That's for logs. How do you get to a fraction? Math alpha, no. Alpha math? No. All right, I don't know how to do it, so forget it. But let's see, just use parentheses, and in the top put your 80,000. Make sure you do enough zeros. For E, use this guy, negative 0.2t. And remember that for t we're using x, of course. Now come down out of the exponent, close parentheses, divide by, and throw the next guy in. So 1 plus 200 e. Negative 0.2x. Okay, again, come down out, close parentheses, and then raise the whole thing to the power of 2, and that ought to work. Now the other thing you want to do is you want to figure out when this thing is equal to 5. So make a second equation now called 5. And I'm going to make that red, just so it stands out a little better. And then graph them together. So there it is. Now it looks like this thing right here would be your answer, but I'm going to use trace, which I normally would never do. But if I just trace over to there, you guys can see that's a time of like 5-ish. And if you look back at our data, we already knew that we would have been at 5 cases, somewhere between 2 and 6. But that's not when the disease is eradicated. That's when the disease is still on the upswing. The number of cases don't start going down till after the 25th day. And so we can see that it won't be down to 5 cases until sometime after the 45th day. So that means that in our calculator, we haven't chosen the right window. We need to take our window and make sure we kick out to somewhere beyond that 45th day. Now technically, they told us it was only good out to 50 days. See here where it says we're only good out to 50 days anyway, so I guess we could set our max to 50 because after that the model becomes untrustworthy anyway. We see the number of cases goes as high as 100, so in the y direction, you may want to kick your y max up to like 1, I don't know, I usually like to go a little higher than the max, but if I graph this, then we see the number of cases and we also see that point of intersection over here. So that second point of intersection is the guy we want. And if you want to, you could just zoom in on that better. Let me try this. Let me pull this guy off so we have it. So there's a copy of that screen. But a better window might be just to go, I don't know, just go 45 to 55. Oops. 45 to 55. And just let your y values go from 0 to 10 because we know we're looking for that 5 cases. So this should put the point of intersection kind of front and center on our calculator screen. Now to find that point of intersection, you go to this calc menu. So you go second, trace. You want intersection, so choose 5. Your first curve is just anywhere on the blue, hit enter. It should automatically hop to the red, say enter. Now your guess just means get as close as you can. And as long as there's only one point of intersection, you could just mash the enter button over and over and over. But there's your answer. It says x is 48.274, so that's it. So from our calculator, we know that the time is approximately 48.274. Use RFT to find on what day this will occur. So it's that many days. Yeah, and that's it. All right, so there is another question now. There's part C. Throw that in the trash. Here's C. Let me get rid of B. Let me get rid of A. So C says find R of 20 using appropriate units. Explain the meaning of your answer in terms of the decay rate of the substance. So again, how's this different? Yeah. All right, so in part A, we already approximated N of 20, right? And that was coming from the data on the table. Remember for part A, we found it to be about 7 cases per day. Now they want us to actually find R of 20. And again, I would say this function is just too complicated for us to really deal with, but our calculator can deal with it just fine. So looking at your calculator, and I hope this isn't too small, maybe I'll make it bigger if I can. Nice. All right, so what buttons are we pressing to make this work? I'll show you. Can we see everything we need to see? Not quite. Oh shoot, I'm kind of messing stuff up over here. All right, so there you go. So I'm gonna second quit. I'm gonna zoom. We need to go back to a window that actually has 20 on it. So sure, I'm gonna zoom 6 just to get back to 10 by 10. But really, I want to go out to 50. I do probably want to go ahead and go as high as the 125 again. And if you graph that, then we kind of see the whole curve. So here's what we can do. If you want to get a derivative, and I don't think I'd ask you to do this on a quiz because I don't really care that you guys know how to push buttons, but to interpret this answer is important. So how do I find the derivative at 20? You just go back into that second calc menu from before, and option 6 is dy dx. So pick option 6, and it happens to have dropped me at 20. Why did it do that? I think it's because that's right in the middle. Yeah, that's right in the middle of my window. If I had started at 0 though, let's just pretend for a moment. If I went second calc and chose 6, it's not going to drop me right at 20. So just so you guys will know, you can, if you tried to just use the arrow, you'll never get right to 20. It's going to hop over it. See, it goes from 19.6 to 20.07. But you can just type in 20 and it'll automatically take you directly to 20. So if you want to be exact, and you definitely do, then do this. And you can see that your derivative is 7.697. So we can jot that down. That r prime of 20 is approximately 7.697. And this again is new cases per day squared. So cases per day. And this time it does say, explain the meaning of your answer in terms of the decay rate of the substance. So what does this mean? That means that on the 20th day, the number of new cases per day is increasing at a rate of 7.697 per day, right? So cases per day. The other thing that's moderately interesting here is remember that the rate of change we got at n from the table, n prime of 20, was 7. So we can see that our initial approximation of 7 was not too bad for an approximation for the actual data from the equation that the scientists came up with. So there. Moving on. So number 3 says, the number of gallons P of T of a pollutant in a lake changes at a rate of P prime of T equals this function, gallons per day, where T is measured in days. There are 100 gallons of pollutant in the lake at time 0. Is the amount of pollutant increasing at time 7? Why or why not? Let's turn this thing off for the moment. There we go. Okay, so how do we do this one? Well, if they ask us, is the amount of pollutant increasing at time 7, then we really are just interested in finding the rate of change of the pollutant, which is the exact equation they've already given us, the P prime equation. So we just want to find P prime of 7, and if it's positive, then yes, we're increasing. If it's negative, then no, it's not increasing, it's decreasing. But that does mean that all we're going to do is take the equation they gave us and just substitute in 7. And again, we end up with some expression that we really can't simplify in any way, so this is fine. You can just leave your answer like this. But do go ahead and approximate that as well. And again, the easiest way would be to put it in your calculator, so I'll bring that back now. Yoink. And we type it in. So we go 2 minus 4 times E to the negative 0.3 times root 7. So if I type it in just like this, is that going to work? The answer is yes, because my calculator understands order of operations. So it's going to do e to this power first, then it's going to multiply by 4, and then it'll subtract. So just entering it in exactly the way you see it, at least on this calculator, will work out fine. So enter. So that's the answer, as far as I can tell, 0.191. And what is that? Gallons per day. And they're asking, is the amount of pollutant increasing at time 7? So you're saying yes, the amount of pollutant is increasing at t equals 7 because p prime of 7 is positive. And that's really all you have to say in terms of your answer to why or why not, is just make sure you're letting me know that yes, it's increasing because the derivative at that time is positive, and that's plenty. That covers every base. I feel like I was going to say something else. What was it? Oh, just for the people that still kind of struggle with their calculators, I think I know how to turn this back. Yeah, so I'm just going to turn off math print, turn it back to classic. A lot of our calculators work more like classic, so yeah, you can see this is my previous entry, and look at all the parentheses they added in now. So if you were typing this in, if you just typed 2 minus 4e negative 0.3 root 7, are you still going to be fine, or do you need to be more careful? It looks like it's prompting you for parentheses in all the right places. So I think even if we do this, you will still get the right answer. But be really, really careful with order of operations and parentheses in your calculator. I hate to see you guys getting these questions wrong when your only mistake is, putting a parenthesis in the wrong place. So if you have any questions about how to do that, make sure you ask me. All right, but that's 3. Let's move on to 4. And I guess turn the calculator off for the moment. Okay, so looking at 4. Use the data from the table to find an approximation for r prime of 40. And again, the data that we see is for r, which is perfect. That means if we want to approximate 40, we're just going to use 30 and 50. And this is a pretty easy question. So we know that r prime at 40 is just going to be approximately equal to the average rate of change between 50 and 30. So we're just going to do r of 50 minus r of 30 over 50 minus 30. And then just pull that data right out of the table. So it's going to be 60 minus 45 over 20, which is 15 over 20. And divide them both by 5, you get 3/4, aka 0.75. So there's my computations. In terms of units, my units would be gallons per minute. So again, it's going to be gallons per minute squared. Because again, we're finding the rate of change of a rate of change. So your denominator is going to get that squared. But that's it for 4. I'm not going to make a mountain out of that molehill. We'll just move on. And number 5 says, a store is having a 10-hour sale. The total number of shoppers who've entered the store t hours after the sale begins is modeled by the function e, where e is this big polynomial. And this polynomial works on the interval from 0 to 10. So at what rate are shoppers entering the store 4 hours after the start of the sale? All right, so if you want to find the rate, then you need to take e prime and substitute 4. So before we do that, though, let's find e prime of t in general. And that's just all regular old power rule. This is going to be 0.8 t cubed and then minus 30 t squared plus 100 t and that's the whole thing, I guess. Then we just plug in 4. So it'll be 0, oops, it'll be 0.8 times 4 cubed minus 30 times 4 squared plus 100 times 4. And I'm not going to pretend that I feel like doing any of this by hand, so we'll just go to the calculator again and do it. Make sure you show the work. I mean, we can do this work by hand, so take it as far as you can before heading to the calculator. That way you'll still get full credit. But yeah, now that we're in the calculator, just type everything in. It's going to be 0.8 times 4 cubed. You know what? If you really want to be a good guy, then maybe you'll show these partial answers. So 51.2. Then the next one. 30 times 16. 480, which I knew that. 480 plus 400. All right, so now what are we doing? 51.2 minus 480 plus another 400 brings us out to negative 28.8. And this is the rate of change of the total number of shoppers who have entered the store T hours after the sale. So this is shoppers per hour. And it says, at what rate are shoppers entering the store 4 hours after the start of the sale? This is the answer, but you know that on the quiz I will ask you to interpret what this means, so you better be ready to say 4 hours after the start of the sale. Total number of shoppers who've entered the store. A store is having a sale. The total number of shoppers who have entered the store T hours after the sale begins, multiplied by the function da 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 da. So yeah, I mean, I guess it's right to say this models the fact that 28.8 shoppers are leaving the store. So there's some shoppers in there already, and then the sale starts and people start coming in and in and in, but then eventually they start to go out. So that's it. So when T equals 4, shoppers are leaving the store. At a rate of 28.8 shoppers per hour. And let me move that calculator out of your way. There you go. But that's it. Honestly, I think these questions maybe were almost too easy because of the way we could just use our calculator to do almost all of it. But that's okay by me, as long as you guys understand these ideas behind rates of change and using them to interpret real-world situations, then we're going to be fine. So that's great. I'll see you tomorrow. Tomorrow will be our last review day before we take a quiz on Wednesday. So take it easy. I'll see you later. Bye.